since I intend that electrochemistry chapter 22 is part and parcel of exam 3, which is next week, because for this unusual calendar year, Thanksgiving comes a week later than usual. That means exam 3 comes earlier than usual. I need to have you folks get at this. I posted an announcement about this yesterday on the Sockeye website. The videos, of course, are on Absolutely Chemistry, 2 different websites. This information is given you on the syllabus for the course. These videos I made this summer when I taught this course. Summer's wonderful. Got more time. Much less rush. You will notice that conversation during these videos is, of course, devoted to the business of the summer class. You can skip past that. After a quick scan, you'll see where the chemistry starts. That's the stuff you need to look at. So, since on Monday, I expect to get at electrochemical arithmetic. In order to get at electrochemical arithmetic, you need to have gotten through the information in the notes on chapter 22 regarding derivation of half reactions, so that you'll know how to derive half reactions from which you can write equations, correct equations for net redox reactions. I need you to do this weekend. It's not a big deal. It'll take you a couple hours of time. X3 next week. Key for quiz 3 is posted. The special quiz key I'll post this afternoon. Now, last time we talked about the best way by far to determine oxidation numbers. Since a redox reaction is easily recognized by examining the reaction to see if oxidation numbers change during the progress of the reaction. So if you're familiar with and know how to assign oxidation numbers, you can easily examine an equation for reaction to determine if it's redox. How about this? This redox? Did you learn that oxidation states, same as oxidation numbers for atoms in elements, are equal to 0? But for the water molecule, even though I expect that you know the oxidation states for oxygen and hydrogen in the water molecule, if you write the Lewis structure, parcel the electrons in accord with relative atomic electronegativities, parceling the electrons at the bond sites, and apply the recipe to calculate oxidation number. After you parcel the electrons, oxygen is -2, each hydrogen is +1. So we're looking at a reaction in which 0 oxidation state hydrogen atoms in the hydrogen molecule are reacting with 0 oxidation state oxygen atoms in the oxygen molecule to make the water molecule. 0 oxidation state hydrogen, 0 oxidation state oxygen, and we wound up with a material in which hydrogen is +1, oxygen is -2 from an oxidation state standpoint. Redox. No more, no less. Now with this, we want you to know the language. Do any of you remember that I asked you to learn this language in 2045 laboratory, assignment 5, part 1? This is important stuff. To me, it's pointless in 2045 to wait to get to this stuff. So, I asked you to start learning some of the fundamentals of this stuff in 2045. And in 2045 lab, I meant to say, not 2045. Do you recall being asked to watch a couple of videos prior to assignment 5? A couple of videos in which a very famous actor offered presentations on fundamentals of redox reactions and fundamentals of Bronsted lauric acid-base reactions. Actor won many Oscars for this. Of course, you know I'm talking about me. If you need to rewatch those videos, they're there on Absolutely Chemistry. You can do so. For the redox video, among other things, we showed you what happens when sodium is added to water. Water's not a particularly good oxidizer, but sodium is one damn marvelously strong reducer. So it's not surprising to find that this powerful reducer, sodium, readily reduces water. Reduction products are hydrogen and hydroxide ion. Oxidation product is sodium ion. You learned in 2045 that these 1A metals, the only chemistry they show is conversion of zero oxidation state element to +1 oxidation state cation. And I trust you recognized that there's a world of difference between the reactivity of sodium, the atom, and sodium ion, which is produced when sodium atom reacts. That seem to be a fair statement? Maybe I told you this before, but I'll tell you now. Again, if I told you before. In 2045, it's important to learn fundamental nomenclature and correlation of nomenclature to these fundamental electron configuration considerations that you make in 2045. The main drive for reaction is what? From an electron configuration standpoint, what would you argue is the main drive for the reaction of an atom? Like sodium, which has got one valence electron, right? Like all the other 1A metals. Or the 2A metals, which each have 2 valence electrons. What's the main drive for these materials to react? Are they, with 1 valence electron, electronically stable? For students who tell me in 2045 that sodium, the atom, Na and Na+, these two formulas mean the same thing. Every student who says that has to come to the front of the class. And every student is required to stick out their tongue. And then I go to every tongue and I sprinkle on some sodium chloride, a material which is rich in sodium ion. And I reel in the tongue. Tell me what you observe. Well, if you're very careful, you will of course get a salty taste, but if you're very careful, you'll observe a little bit of cooling. Because sodium chloride, like most ionic compounds, dissolves endothermically in water. Okay? Be a little bit of cooling. But that's about it. No big deal. Yet you just placed upon your tongue a whole lot of sodium ions. All right? Tongue's back out. I walk along with a squirt bottle, I rinse off every tongue. Now I come along to every tongue, and I take about 1 gram or 2 of sodium on every tongue. Reel it back in. Now tell me what you experience. Pow! Jeez, no more teeth. No more mouth. Can't tell me anything. But never again will that student tell me sodium and sodium ion are the same thing. Because what that sodium atom did was to get rid of one hell of a bunch of energy so that it could eject its valence electron and in so doing become isoelectronic with its nearest neighbor, noble gas neon. I like the way that rolls along. Because the main drive for reactivity of atoms, which you learned in 2045, is to rearrange their electron configurations by reacting until the electron configuration becomes that of a noble gas. How about that? That's pretty much where it all lies. Okay? So this is what I talked about in this video for 2045 Lab Simon 5 Part 1. That chemistry is exhibited by this sample half reaction. A half reaction which exhibits the process called oxidation. Redox. A combination of reduction and oxidation. Like an acronym of sorts. Reduction. Half reaction showing decrease in oxidation number, oxidation state. Oxidation, increase in oxidation state, reduction, decrease. Like sodium becoming sodium ion by losing one electron per sodium atom. Like chlorine atoms in the chlorine molecule collecting one electron per atom to become chloride ion. This stuff is now isoelectronic with neon. This stuff is now isoelectronic with argon. And that's where their reactivity stops, because now electronically they are very stable. Now you can get those things to react, but you're going to have to spend a lot of energy to get them to react. Like you can take sodium chloride, melt it, and turn it back into sodium element and chlorine the element by electrolysis. But you've got to put in a lot of energy to make this happen. Because you're fighting, in that case, the great stabilities of sodium ion and chloride ion respectively. Now then, how do we get the net redox reaction? You simply take these puzzle parts, the half reaction showing oxidation, coupled with the half reaction that shows reduction, and put them together by a process called coupling, which we'll talk about extensively in a moment. So I'm putting together the oxidation half with the reduction half in a systematic fashion, as exhibited for this set of half reactions. What's the systematic fashion to which I refer? Notice that in coupling these two half reactions, I took the sodium-sodium ion half reaction, multiplied it by 2. I could have done the same thing by leaving the coefficient of 1 on the sodium-sodium ion half reaction and multiplied this by a half throughout. Because it's absolutely impossible for any bulk system to be stable if it contains an excess of charge. That's impossible. So I cannot write an equation for a net redox reaction which makes any sense if it has residual electrons as reactants or residual electrons as products. So in this coupling process, you'll have to apply coefficients to either the oxidation half reaction or the reduction half reaction or both, so that when you add up these two half reactions, after adjusting the coefficients, you get no net electricity as reactants or products. Nothing fancy about this. This then becomes the net redox reaction for coupling of these two half reactions. This leads to more language. Language which again I asked you to learn about in 2045. The reactant components of a redox reaction are known as the reducer and the oxidizer respectively. The reducer, if I am the reducer, I'm going to react with something called an oxidizer and make my oxidation state increase. I'm the reducer. I experience oxidation. But I'm the reducer. So I'm going to push electrons onto you, or whatever the oxidizer is, and make your net oxidation state get less positive or more negative. You're the oxidizer. You took these electrons from me and caused me to get oxidized. So these two parts, reducer and oxidizer, as reactants in a half reaction. correspond to the reducer experiencing oxidation as it reduces the oxidizer, and the oxidizer experiencing reduction as it oxidizes the reducer. You probably say, oh, I don't these damn words. It's perfectly sensible terminology. But don't get hung up on trying to say all this stuff like I just did. Just look at the equation for the redox reaction. And recognize, for example, in this redox reaction, given that in the material sodium chloride, the oxidation state of sodium is the same as its charge, +1. The oxidation state of chlorine is the same as its charge, -1. So here's 0 oxidation state sodium becoming +1 oxidation state sodium ion. That means this got oxidized and means it is the reducer. Correspondingly, chlorine, 0 oxidation state, became -1 oxidation state chloride ion. So this stuff got reduced. That means it's the oxidizer. Now what about the language applied to the products of a redox reaction? The oxidation product, the reduction product. For this redox reaction, there's only one product, sodium chloride. So sodium chloride is the oxidation product as well as the reduction product. Now, if you went on to say that sodium chloride is the oxidation product because it contains the material which was produced by oxidation, namely sodium ion, that's fine. And if you went on to say this is also the reduction product because it contains the material which was produced by reduction, that's fine. But this is the oxidation product as well as the reduction product. Like in this reaction for hydrogen getting together with oxygen to make water. This is the oxidation product as well as the reduction product. It's the only product. What else could it? I mean, it has to be both. What's the reducer here? What stuff experienced oxidation? Hydrogen. Went from 0 oxidation state to +1 oxidation state. So hydrogen in this reaction is the reducer. It experiences oxidation. Oxygen in this reaction is the oxidizer. It experiences reduction. And you may well have guessed that this oxidation term came because a long time ago, when chemists first started to learn about this kind of stuff in the early days of chemistry, they thought that oxygen was the only oxidizer. Of course, they quickly found out there's a whole bunch of different oxidizers. Not just oxygen. They thought that every oxidation required interaction with oxygen. Or every redox reaction required interaction with oxygen. Long time ago. Now then, you remember how much information we were able to get from and also be able to use from the acid-base table? I hope you do. Now let's take a look at our half reaction table. Open the notes right now. Pages 22, 4, and 5. This table's a lot longer than our acid-base table. But practically speaking, it is to be read in the same fashion. You look at this table. Remember the acid-base table. Listed. Acids in the left column, bases in the right column, and the base positioned immediately horizontally to any acid was the conjugate base of that acid. Or if you look at the base column, you could also say that each acid horizontally positioned immediately to the left of the base in question is the conjugate acid of that base. Okay? So look at this table and recognize that unlike the acid-base table, in this case we do see a difference. And of course this is not an acid-base table, this is a half reaction table. There's a reaction arrow because this table is a table of half reactions. So on the left side of each reaction arrow, the way I have written this table, table 2 in our notes, on the left side of each reaction arrow, for this table as written, you'll see the formula for a reducer. And on the right side of the reaction arrow, the product of the half reaction, you'll see the oxidation product. The stuff produced as the reducer on the left travel across the reaction arrow to become the oxidation product on the right. Now then, do you remember in the acid-base table? The acids were listed in order of increasing strength from bottom to top. The strongest acid in our acid-base table was the one at the top of our left side acid column. In this table, the strongest reducer in the table is lithium. Do you see it? Top left of the table in half reaction number 1. So look at the tail end of the table and tell me the weakest reducer listed in this table. Fluorine. Practically speaking, if you want to make fluorine, you have to make it by electrolysis. You can't make it chemically. How are you going to make it chemically if it's the weakest reducer there is? I mean, pardon me, how are you going to make fluorine chemically if fluoride ion is the weakest reducer there is? Right? That's what you see at the end of this table of half reactions on the left side. You see fluoride ion, don't you? Becoming oxidized to fluorine. So again, just like the acid-base table, the strongest acid, top of the acid column, the strongest base, bottom of the base column. So look at the table, and now tell me, which I just told you, but tell me anyway, what's the strongest oxidizer in this table? What is it? Fluorine. And in this table, what is the weakest oxidizer? Lithium ion AQ. Don't forget the phase. That involves chemistry. We have to pay attention to phase in this case. But as usual, we're going to do everything either with pure substances or aqueous phase when we deal with solutions. We're not going to do any kind of solution except aqueous phase. All right, so we're looking at this table. 45 half reactions, is that correct? It's 45 or 44. Okay? Question. With this table, where you see a collection of 45 half reactions, from a thermodynamic standpoint, with this table, the outcome of how many redox reactions can be predicted? How will you answer this question? Let me tell you how to answer the question. If we have an acid-base table composed of just 2 acids and correspondingly 2 conjugate bases, discounting any reaction of a reducer with its own conjugate oxidizer, discounting any reaction of an acid with its own conjugate base, because reaction does occur between these two, but it doesn't change composition of system. With this table, the outcome of how many acid-base reactions can be predicted? 2. HX plus Y minus gives you a reaction to produce HY and X minus, which is extent Y is large or small. On the other hand, HY with X minus, which will give you HX and Y minus respectively as products, is also an acid-base reaction whose outcome you can predict. Will it be large or small extent? Small. Okay? Now look at the table. Now as you look at the table, I want to make one more comment. Unlike acid-base reactions, Redox reactions are generally reactions which have, if they are reactions which go spontaneously, huge K values. That means practically they're one-way streets. Practically they're 100% completion reactions. So if you put together a reducer with an oxidizer that's capable of oxidizing that reducer, like if you put together sodium with chlorine, hey, that's one-way street. If you put a mole of sodium with a mole of elemental chlorine, number one, get the hell out of the way. Because boom is going to happen, and you're probably going to fracture the reaction vessel in which you conducted this investigation, and you're going to wind up with, well, I said a mole of sodium, 2 moles of sodium and 1 mole of elemental chlorine. You're going to wind up with 2 moles of sodium chloride. If you use 2 moles of sodium and a quantity of chlorine less than 1 mole, boom! Do you think there'll be any unconsumed chlorine remaining? No, but there will be unconsumed sodium. Because that thing tells you if you're going to run this reaction using 2 moles of sodium and you want to consume all the sodium, you need a mole of chlorine. So if you've got less than a mole of chlorine, you'll consume all the chlorine, but you won't consume all the sodium. Remember a concept that you learned about in 2045 which relates to this? Remember limiting reagent? Or limiting reactant? Same thing. Okay. But again, the main difference with redox reactions between acid-base reactions is HY plus X minus is likely a reaction for which we'll have an equilibrium constant that will tell us if HY reacts with X minus, we can calculate the amount of HX and Y minus produced by this reaction. But for redox, as with sodium with chlorine, you put together these in a ratio of 2 moles sodium per mole of chlorine, there won't be any unconsumed sodium, won't be any unconsumed chlorine left behind. All right? So back to the question. How many redox reactions can you predict the outcome of with this table? Well, let's look at 1 and 2. 1 and 2 in the table says lithium will certainly reduce calcium hydroxide. Okay? But practically speaking, calcium metal cannot reduce lithium ion. That's what we just said, because these are pretty much one-way streets. But you can predict the outcome based on what we just talked about. K values being very large, or if you put together a reducer with an oxidizer that's incapable of oxidizing that reducer, like lithium ion with calcium metal, not going to oxidize calcium metal with lithium ion. That's 0 extent, but you can predict the outcome. So with 1 and 2, just like with 1 and 2 here, you can predict the outcome of 2 reactions. So how many total redox reactions can you predict the outcome of with this table? Here's the answer from a numbers standpoint. We got 45 half reactions here, don't we? Okay. That means you can predict the outcome of lithium with every oxidizer in this table. Every one is practically speaking a 100% extent reaction. Just like you can predict the outcome of calcium in the presence of hydroxide ion. With every oxidizer in this table, everything you see on the right of a reaction arrow. You can predict the outcome that calcium won't do anything with lithium ion, but it'll beat the living hell out of every other oxidizer underneath calcium hydroxide. How about that? Now, coupling. Look at the table. We're going to think now about assembling an electrochemical cell which will deliver usable electrical energy. From the table, you can make such a cell by taking any half reaction you want and selecting another half reaction which meets the requirement of being positioned in the table lower than the first half reaction you selected. Pick any half reaction you want and pick any other half reaction in the table that's underneath the half reaction you picked, someplace underneath. This will correspond to a half reaction of higher E0. That's the one at the top that you picked. Coupled with a half reaction of lower E0. That's the half reaction that's listed underneath someplace. Now, if you remember, reducer strength in the table is increasing from bottom to top, while oxidizer strength is increasing from top to bottom. For the two half reactions you selected, the one with the higher E0 value will remain traveling in that direction. The half reaction with the lower E0 value will be run in reverse. You turn it around. Because what you have done is to couple a reducer with an oxidizer that's capable of oxidizing that reducer. On the other hand, if you take a half reaction from the table and couple it with a half reaction that's listed above, then you will have to recognize that the reducer from the first half reaction you selected, the one of lower E0 value, cannot be oxidized by the oxidizer from the second half reaction you selected. Now, all this sounds like too much talk, so let's do an example. Specifically, consider these materials. Zinc solid, copper solid, 1 molar zinc sulfate solution, 1 molar copper sulfate solution. That's the end of the chemistry. Beakers, wire, salt bridge. And in the table, see half reactions 18 and 32. Half reactions 18 and 32, respectively, show zinc in the presence of water being oxidized to this stuff, hydrated zinc ion. You might recall hydrated zinc ion also appears in our acid-base table. The second half reaction, number 32, as it is written in the table, shows copper being oxidized in the presence of water molecules to make hydrated copper ion. Right? You see that table? So keep in mind what we said. To play this coupling game, in order to give us an electrochemical cell that will give usable electrical energy, for the two half reactions you've selected, in our case 18 and 32, you keep the half reaction that's above, the one of higher E0 value, in this case zinc going to zinc ion. You write that as it is. And you take the other half reaction, in our case that's number 32, you turn it around. Because what we realized in considering coupling these two half reaction systems is that zinc can reduce hydrated copper ion. Put another way, hydrated copper ion is capable of oxidizing zinc. But can copper reduce hydrated zinc ion? No. Now maybe you remember, you did this in 2045 lab. I had you do this. Because if you have two potential reducers, like copper and zinc, and you don't know which one is stronger, you do a simple chemical test. You take a solution which contains the conjugate oxidizer of each of these reducers. For zinc, that's hydrated zinc ion, if we're considering this occurring in water, okay? And for copper, that's hydrated copper ion. Likely in 46L, you've already seen this stuff. Hydrated copper ion, nice, pretty blue. All right? So now we've got a copper ion containing the solution, copper ion being the conjugate oxidizer of copper for the oxidation occurring in water, and a beaker containing hydrated zinc ion, the conjugate oxidizer of zinc for oxidation conducted in water, and my two potential reducers, zinc and copper. Which one is stronger? Well, let's find out. I'll put my my copper strip in the beaker containing the zinc ion. Because if zinc ion can oxidize copper, then something's going to happen here. I'm going to deposit zinc metal on my copper strip as the copper gets oxidized to hydrated copper ion and gives me this blue color. If we let this stand here for a year and a day, or eternity, you're not going to see any blue color develop here. Because because zinc ion is not capable of oxidizing copper. Well, then it must be true, because zinc and copper can't have the same ability to function as reducers. So we already know, if copper cannot reduce hydrated zinc ion, then zinc has got to be able to reduce hydrated copper ion. Just like the acid-base table. I covered it up. If HX and HY are two different acids, well, the conjugate base of these acids, one of them's got to be stronger than the other. Same thing here. So here's my zinc strip. I'm going to just touch it to the copper ion solution. Now look what I've got already. A bunch of copper black. If I leave the zinc strip in here for any length of time, you'll see the characteristic bronzish color of copper develop. But this reaction happens so fast and to such a large extent that I've made a bunch of copper atoms but have not given them the opportunity to get together and develop the customary copper lattice, which will show us the bronzish color. If I leave the zinc strip in the copper ion solution for a couple minutes, you'll start to see the bronzish color develop. So we have discovered zinc is a stronger reducer than copper, and hydrated copper ion is a stronger oxidizer than hydrated zinc ion. And that's the way they're listed in the table. Now, how do we use these materials to make us an electrochemical cell which will be able to deliver usable electrical energy? Because if I have my zinc reducer in direct contact with my oxidizer hydrated copper ion, I have what's known as a short circuit. The electrons flow immediately from the zinc atoms to the copper ions, causing the deposition of copper atoms on the zinc strip surface. I'm already starting to get a little bronzish color here. Okay? It's a short circuit. We can't make batteries like that. You've got to make the electrons, which in this case flow from the zinc atoms into the copper ions. You've got to make those electrons travel through an external circuit. That's the way you make a battery. So let's see if we can make a quick, fast battery out of this system. I had a bunch of zinc and copper strips in the back, but somebody took them. I don't know who that somebody is. I got an idea. We'll have a talk about it later. I tell people back there, look, use any of this stuff, but put it back! The put back part has not yet been met with. Okay? What we do is to take the reducer in question, and in this case, put it in contact with its own conjugate oxidizer. That's zinc iron. And take the poorer reducer, which in this case is copper, and put it in contact with its conjugate oxidizer. Copper touches hydrated copper ion. Zinc touches hydrated zinc ion. Okay? And then we're going to connect the metals, the zinc metal and the copper metal respectively, so that they will be able to function as electrodes. You know what electrodes are? What do you think an electrode is by definition? How about a current carrying device? Is that fair enough? Electrode, current carrying device. Okay. So, maybe I'll hook them up backwards. If I hook them up backwards, then I'll reconnect. I got my wire connected to zinc, and another extension of the wire connected to copper. And in this case, the wires themselves are connected to this gadget, a voltmeter. This doesn't read current, it reads volts. Okay? Now, if I turn on the voltmeter now, I won't get a reading. Why not? Well, I provided the opportunity for electrons to flow from zinc through the wire, through the meter, into the copper strip, which will transfer the electrons to the copper ions. And if copper ions collect the electrons, they will now deposit as copper atoms on the surface of the copper strip. But how the hell can the electrons get back? I have an open circuit. I have to meet the physical requirement of having a closed circuit, a complete circuit. You did this in physics class, I bet. So, as a demonstrational device to complete the circuit, we use a gizmo called a salt bridge. I got some salt bridges here. They're not very good, but they'll serve the purpose of giving us a connection. I don't like that one too much. Let's try this. In this case, as far as I know, as you see, I stuck my hand in there. Not dangerous. This is saturated sodium sulfate paste. That's inside the salt bridge. Because in the salt bridge, we need a medium that's rich in mobile ions. Because flowing ions are current. Anything charged particle flowing is a current, okay? So I'm going to see about getting a reading by connecting my two beakers with the salt bridge. Okay. And what I'm getting here is about 1.06. Can you see the reading for those of you up close? This is a voltage reading. Now, if this was operating perfectly, maybe I got this connected backwards. I don't know. Let's try it this way. I'd get a reading of 1.1 volts. You'll see this. Yeah, now we're doing better. Oh. It's about 1.08 now. Okay? So you look at these videos, and we'll pick it up from this point on Monday.